Okay, so we're back to actually get to the chunky bit, the analysis. Now, if you've got a lot of graphs open, there is an option to close all graphs. Occasionally get people show me minitab projects with hundreds of graphs in them, and you probably don't need them all. There is an option to turn off that check save. When you close a graph, it always asks you if you want to save it by default. So under graphics, graph management, I changed that to don't ask me to save it. One, because I can always generate the graph again, and two, I usually save the graph separately if I want it anyway. So I would change that just because it's slightly less annoying. Right, so we're going to do some analysis. For this part, I'm just going to look at height because this is the simple one. Relatively simple, and we're going to look to see if there is a difference between how much soft drink fizzes depending on what type of soft drink it is, how much bicarb we drop into it, and the height that we drop the bicarb from. So we've got three factors that we think are going to affect our response, and our response is continuous. So this means that we can use a general linear model or an analysis of variance. Now, ANOVA is actually sort of sits inside a general linear model. That's basically what a general linear model does anyway, but it just gives you a few more options. So if you're confused about what to do, I would go straight to the GLM. What not to do, don't run a whole lot of one-way analysis because you can do it all together, and it's a better analysis because you're taking care of everything all at once rather than testing using a one-way analysis, testing soft drink by itself, then testing drop by itself, then testing bicarb by itself. You can use a balanced ANOVA because in this case we do have a balanced design. If you run the model both ways, you'll find you get pretty much the same results. I think you get exactly the same p-values anyway. It's always possible when you're using different options that the maths behind it is just a little bit different or more efficient, so you may get slightly different p-values with different types of tests, but if broadly speaking it's the same model, then it won't matter which option that you use, except that you can't use a balanced ANOVA if your data is not balanced. So I usually stick with the GLM by default. Because I've already done it, everything's already sitting in here. So we're going to look at height. I'm going to delete these out and talk about them one at a time as I add them in. I'm not interested in the relationship between height and time at this case. If I was, then time would be a covariate. It would not be part of the model. We don't have any random factors. These are ones that have all been fixed, and so all of the model is in fact going to go into this box. So we've got type of soda, the height of drop, and the amount of bicarb. Now, something that we noticed when we were looking at the box plots was that the effect on the height of the fizz seemed to change depending on which combination we had of soda, drop and bicarb, so suggesting that these things don't always have the same effect when you're using them in different combinations, and these interaction effects. So to test for interactions, we have to actually put them in again. We'll have to put in type of soda star height of drop, and that means test for an interaction between soda and height of drop. Then type of soda star amount of bicarb, so test for that interaction, and then height of drop star amount of bicarb and test for that interaction. So we can test for a whole lot of things all at once. We can only do this because the students replicated their data. They took 3 observations at each combination of factors. If they hadn't collected so much data, we wouldn't be able to do this. So if you try this with a different data set and it pops up with an error, it probably means you don't have enough data. We're not going to use a covariate at this stage. We do want to look at our residual plots because every analysis that you run will have some assumptions behind it, and you really need to check that those assumptions haven't been violated. Some of the assumptions you can check before you run the model, and some of those assumptions you need to actually check on the residuals, which is the bits left over after you've created the model. So it's a little bit counterintuitive that you assume something but then you can't check it until it's already done. We're going to go for the standardized residuals, and the 4 and 1 plot is a good place to start. if we had some covariates, I might do some residuals versus the variables. Or if we had factors at more levels. I'll leave it in this case. We might go to that for time. If it turns out you have a problem with your residuals and you need to do some further checking on them, you might want to actually save them and store them in a new column, and then you can do more tests. We don't really need to do that in this case. And I'm not going to do any plots straight from here at the moment. Later we'll come back and we'll have a look at some pairwise comparisons, but we'll leave that for now. Okay, so the first thing I'm going to look at are the residual plots, just to see if there's any obvious problems with the model before we go any further. So the assumptions with the general linear model is that the residuals are all the bits that are left over after you have fit the model. And the assumptions are that these are normal and that they're basically random. So we've got two plots here which check for normality. Now if you want to do a proper normality test, you can, if you save these residuals, and you can get a p-value out for it, and that will be under basic statistics normality test. I'm happy with this at the moment. If these dots follow an approximately straight line, and it actually draws the line for you, then it means it's following a normal distribution, and that is looking pretty nice to me. I'm not too worried about this little divot in here. That's looking pretty normal. It doesn't look terribly skewed out in one direction, which is usually what will happen if your data has problems. And are the residuals random? So essentially you're looking to see are there any patterns left over in the data that you haven't accounted for in your model. In this case, I can't see any patterns there. That looks fairly random. There doesn't seem to be any increase in variance with the fitted values. The observation order is quite interesting. There's not much here to see, but it's just because of the way the experiment was designed, I know that the students did not randomise the order of their trials. So when they opened the bottle of Coke, they were worried that the gas would escape, as carbon dioxide does. And so they wanted to do all the trials for Coke at once. So they didn't randomise anything. So all the observations are actually in order. That would be a clump of Coke and then whatever they did next and whatever they did next. It's always good to put your observations, enter the data in the order that you collect it, because then if there are any problems, it will come out here and you'll be able to see straight away that something happened over the course of the afternoon when you were collecting the data. Maybe something was getting gradually longer and longer, and you'll see these patterns come out here. So the residuals for height are looking fine. So now we'll just quickly check one more assumption, and that's that the variances for the different groups are equal. This doesn't come out automatically with your general linear model analysis, unless there was a box somewhere I missed, but you can run it from the stat menu, anova, test for equal variances. So you just need to put in your same model here. I'm not going to put in all the interaction terms. I'm just going to put in the main terms. And here we do get some p-values. So with these residual plots, I'd call that just eyeballing the data to see if it looks okay. Here we've got a p-value we can look at. The null hypothesis for the test for equal variances is that the variances are equal. If you have high p-values, it means you have no evidence against that hypothesis, and therefore you can fairly safely conclude that the variances are equal. There are two tests here, the Bartlett's and the Levine's. I would mostly look at the Levine's test. I'm not an expert on these tests, but the Bartlett's test is a lot more sensitive, and so you're more likely to reject your hypothesis with this one, and perhaps unnecessarily, because the general linear model is fairly robust. You have to have some pretty serious things go wrong with your data for it not to work well. So I have no problem with my equal variances, so I might put that as a footnote or something in the report. And then we can actually have a look at the analysis and see what the results are. That's their equal variances. I'll just maximise this and scroll up. Okay, so here's the output that we're interested in. General linear model versus type of soda, height of drop and amount of BCS. Now I have treated these as factors with fixed levels. If you had a lot of levels for bicarb, say, you may want to treat that as a continuous variable, but then you'd have to be careful about the shape of the response. I don't think it will be linear in any case, so we'll just treat these as factors. In the analysis table here, we have one hypothesis for each line and a p-value. So the hypothesis for this first line says the null hypothesis is that there is no difference in the height of fizz between the different soft drinks when the other factors are accounted for in the model. The p-value is very, very small. The p-value is the probability of getting the data if the null hypothesis is true. So this says that the probability of getting the data that we got, or the students got, if there was in fact no difference between the soft drinks, is almost zero. So that would suggest that the hypothesis is wrong, and in fact there is a difference between the soft drinks. It's very circular reasoning almost, in that you're testing something that you're not interested in. But that's the way the maths behind the test works, is that you can calculate the probability of something specific, but you can't calculate the probability of a very vague statement like, oh, I think they're all different. That would be very difficult to do. But you can calculate the probability of getting the data if everything is the same. And in this case, the probability is low, so they're probably different. So we've got the same hypothesis, or similar one for height of drop and BCS. Then we've got some interaction terms, which we might come back to. We'll see how long this video gets. Then we have the R squared and the R squared adjusted. So the R squared is the amount of variation in the data explained by the model, and the adjusted value has been adjusted for the number of factors and the number of observations. So this is the one that you want to look at. If you only had, say, 2 data points, and you had one explanatory variable and you just drew a straight line between them, it's possible you would explain 100% of the variation in your data, and that would give you a massively high R squared. But it's very easy to join up 2 dots with a line. That doesn't necessarily mean you're explaining much of what's going on, and the R squared adjusted will take account of the fact that you only had 2 data points and you were only trying to fit one factor to them. So in this case, there's not a lot of difference between the R squared and the R squared adjusted. So there's no evidence that we're overfitting the model. We've got a good date. We've got 71 total degrees of freedom, and you can see which each of the factors is taking up. We have a couple of unusual observations. I'm not too worried about them. I'd be worried if I had 20 unusual observations. That might mean I need a transformation to sort of tidy up the data a bit. We could go through and check what happened. It's possible that something went wrong if one of them was extremely large. So if this was an unusual observation and the time, instead of being around the 20-second mark, was around the 1 minute 20-second mark, that might mean that someone actually forgot to turn the stopwatch off. And again, there's another one at observation 25. So we could go back and check the data collection sheets to see if there was anything obviously wrong with them. Otherwise, I just leave them in there. You shouldn't delete data for no good reason. Okay. So once we've got the analysis and we look through and we see here that indeed the type of soda, the height of drop and the amount of bicarb are all significant, and we see that all these interaction terms are significant, we'd want to investigate these a little bit further. I might do that in the next video. So what I'll do is I'll look at these first 3, which are called the main effects, and then the second 3, which are called the interaction effects.